Good afternoon, class. So we will be doing TCP congestion control today. We're going to recap flow control from last class, and I would like some kind of feedback from you if I am audible and everything is going okay. Is my screen visible and my voice is clear?
Yes, miss.
Okay, thank you so much. So please do unmute your mic anytime you want to say something because on my screen, all I see is the PowerPoint that I'm projecting. You just please just unmute and ask me a question whenever you need to. And I will also have pauses for questions during this presentation. So let's start off with a recap. And so what we did the last time was flow control, and we said that we will most certainly, we were worried that the channel from sender to the receiver, which is actually many channels, should be utilized to a maximum, which is why we said that we will send out as much data as the bottleneck bandwidth of any part of this channel will allow us, so that we are not underutilizing the space that is available. But then we said that that is not our only constraint. Our second constraint is that maybe the sending host and the receiving host have different capabilities. They are heterogeneous in their capabilities, which means that the sender can send at a faster rate, but the receiver is slow at its end to process data, and we can end up overwhelming the receiver. And that is why we said that there needs to be some feedback mechanism in place that gives feedback to the sender that the receiver cannot keep up with this rate. And if the receiver cannot keep up, it is going to keep on storing the packets that are being sent, and that storage space is then we're going to run out of that storage space, and eventually that buffer is going to start dropping the packets. So the sender will then we will then be stuck in an endless loop where packets are dropped at the receiver and sender has to retransmit them. More packets will be dropped at the receiver. So this is absolutely ineffective. So what we said was that we must. So one question that I put to you to just to recap what we did in the last lecture is, um, we said that we will have a buffer at every host to buffer the packets that are coming in. So this is the TCP buffer that is decided at connection setup time. So my question to you is, what can be the possible reason why data could need to be buffered at the TCP receiver buffer? So we said that both the parties, it's a full duplex channel. Both the hosts are sending and receiving data from each other. So at some point in time, every host is the sender and every host is the receiver amongst the two of them. So there is a receiver buffer at both hosts. And what is the possible reason that data would need to be stored in this buffer? Can somebody help me out? So this is like the buffer that is set up per TCP channel, per TCP connection at connection setup time. So every time a TCP connection is established between two hosts, there's a buffer that is set up and the space is communicated at setup time, right? And there is some buffered data, and you see the blue area is the buffered data. So some packets are buffered, and there is still some space in which future packets or arriving packets can be buffered. Right? What is the possible reason? Why would data need to be buffered? Why is it not just handed over to the application? Any possible reason for buffering?
To prevent buffering on receiver's end.
Sorry, can you say that again?
To prevent buffering on receiver's end.
This is the buffer at the receiver. So this is the receiver end. And the receiver end is not some special end, because two parties, when they're talking to each other, they're continuously exchanging data. I hope you understand that. So there's no one designated receiver. You are a receiver when you are receiving data, you're a sender when you're sending data. Is that clear?
Yes. Okay.
Could it be
Why?
we
Yes,
deal with
please.
out of order packets, especially during retransmissions? And at the sender's end, it could be to store the data packets until we have enough of them to transmit them.
Absolutely. It could be, thank you. So at the receiver end, you could get out of order packets. Please remember that TCP has chosen selective repeat. And selective repeat says that we don't necessarily have to discard packets that come out of order. So we keep on buffering them until we get the missing packets. Once we get the missing packets, then we send the or data in order to the application. So that's absolutely correct. That is one very probable cause why we need to buffer data, even at the sender's end. When packets are coming in and you need the line empty to transmit the next packet. So you could temporarily buffer the packets if they're coming in at a very fast rate from the application. So there are buffers at both end, right? And the receiver especially buffers the data when they're out of order, or sometimes they're coming in at a very fast rate and maybe the TCP processing is taking longer, and you need to buffer them temporarily until all of them are processed and then shipped off to the application process. So that is absolutely correct. And then there's a second question, which has two parts. So, part A says that, so if you see in this diagram, we have here that if this is the entire space of the receive buffer, I have marked the free space as the receive window. This is marked as the receive window. So, what we discussed last time is that the receiver has to give the sender some feedback that I am capable of receiving more packets. I am not being overwhelmed. I'm fine. So, if there is free buffer space, the receiver will send the number of bytes of free buffer space to the sender to tell it that I still have buffer space. That means I am coping with the data rate very well. And we also discussed that if the receive window is advertised or sent back to the sender as 0, that means that the whole buffer is full. There is no space to buffer packets. We also discussed what the sender should do in that regard. We'll go over this again. So, my question to you is, if receive window, this RWND, um, which is what is sent back to the sender as feedback, it's the free space or the number of bytes in the receive buffer. How many bytes should the sender send out? ये जो feedback मिल रहा है receive window की number of bytes में, um, how should the sender respond to this? Sender को किस तरह respond करना चाहिए? अगर उसे पता चल जाए कि so many free bytes are remaining in the buffer, how should it dictate the sender's sending behavior? Gee, that's a question to you guys. Please, Rabia.
It should decrease the number of packets it sends to a quantity that is either equal to or less than the free space available.
So, of course, the sender is then advised to restrict its sending to the space available at the receiver. So, now we have two aims that TCP is trying to keep up with. You remember the first aim, we're going to come to that in a bit. Let me go to part B first. What happens when the sender sends more than receive window? If the receive window advertised, for example, if the receiver advertised or sent feedback back to the sender that I have 1000 bytes free in my buffer, what if the sender sends 2000 bytes to the receiver? What will happen?
It
So
will
the
be dropped.
receiver said, I have only 1000 bytes. Please go on. Sorry.
The packets will be dropped, the extra packets.
Absolutely. So only 1000 bytes can be stored in the free buffer, and the rest of the bytes have no space. The buffer is full, so they will be dropped. So thank you. So let's just actually just put a closure onto this. This slide will hopefully cover all ground. So the receive buffer size is set at connection setup. We've already done that. The TCP receiver communicates or advertises the free buffer space in this field that is called rwind or the receive window. This is a field in the TCP header and it is sent at connection time, right? Now, the window size that we discussed then, if you remember, here we said that the window size should be bandwidth times RTT. What were we trying to do? What was this? This was the bottleneck bandwidth. This was the bottleneck bandwidth. What were we trying to do with this equation? We were trying to fully utilize this. So what we were trying to do was fully utilize it. That was our aim. So we were trying to adjust our sending rate such that we fully utilize the bottleneck bandwidth. But now we have another player in the game. And the other player is that we can be restricted by the free buffer space at the receiver. That free buffer space, how is it communicated to the sender? The buffer space is communicated via this field in the TCP header. And this field keeps on changing. So as the data from the buffer is processed and sent back to the application, more and more of the buffer space is being freed. So this is continuously being communicated as TCP packets are exchanged to and fro between both the hosts. All right. So this information that is continually being updated, this information, just like you remember, RTT was continually being updated by the moving average. We had a moving average. We know that the RTT, this is not static. So we were continually updating RTT to have a good estimate of what it is currently. Here we have, this is changing constantly and it's being communicated, changing and communicated constantly as data is being exchanged. There is room for this in the TCP header, right? So we said that if both of these are players and both of these are constraints, we should go by the minimum of the two. Because if we violate receive wind, packets will be dropped. If we violate bottleneck bandwidth, then we will choke our bottleneck bandwidth link, right? And we will grow buffers before that bottleneck bandwidth link. So that's not good for us. All right. So we choose to go the minimum way between the two. Do I have any questions here? Please feel free to ask a question. Also, this is called the receive buffer. I hope that everybody is now on page that both hosts are receivers and senders in a full duplex link. This is a very important point. They are both senders and receivers. So this is a plus, right? So because you're continuously exchanging data between the two hosts. And our very favorite example is that of loading a web page where we are communicating with the host. We are requesting things from the web server, and it is continuously sending us objects that can help us render the web page. So if there are no questions, let's move forward. So the window size, how does TCP sender decide the window size for maximum utilization to fill up the entire RTT? We said that the window size should be quite easy, bottleneck bandwidth times RTT. And for flow control, we said that we must not ignore receive window here because receive window is telling us how much free space there is. If we ignore the free space, that just tells us that we are not paying heed to the amount of free space at the receive buffer. If we overflow that buffer, then again there's packet loss, and that's very ineffective. So we said we'll go the minimum way for both bottleneck bandwidth and receive. Whichever is minimum out of these two, that will be the chosen sending rate by the sender. And both of these things are continually being updated, right? So as time goes by, they are continually being updated in whichever out of these. So at one point in time, one of them will be the minimum. At another point in time, the other will be the minimum. Whichever is the minimum, the window size is decided just by this. These are the two players that we've come to so far that determines the sender's behavior while it's sending, the sender's behavior that is actually acting on the sending rate towards the receiver, right? But these are not the only two players here. What can still go wrong? Now we're taking care to fill up the bottleneck bandwidth so that we do good link utilization. We are careful that the receive side buffer is not overwhelmed or filled so that packets are not dropped at the receiver end. What can still go wrong? Anyone? Okay, let's move on. This is a picture that I wanted to show you. It's a horrific picture, if you ask me. The fact that we have a lot of people outside their cars, that means this has been the state for a long time. And a lot of us have been in similar situations here, and it's not pleasant. So I will put two questions to you. One, what makes congestion worse? Now, I want you to just take this analogy of the road and cars. This particular congestion, what will make it worse?
More cars.
Anyone? More cars. So if the channels feeding into this big highway, if they keep on sending, if more cars keep on coming this way, this congestion will obviously get worse, right? What would relieve the congestion? What could possibly make it better?
More space, I guess.
So can you stretch the highway, Bilal?
No.
So what else can you suggest then?
Stop the incoming cars.
You could divert the incoming cars to other alternate routes, right? So obviously there is some choke point ahead, and that choke point is actually putting pressure on the amount of vehicles that can go through that choke point, right? If you can relieve the backlog, if you can somehow stop the rate of the cars coming in, you would slowly be able to relieve this congestion. In the other case, if you keep on sending cars along the incoming channels, this congestion will most certainly become worse, right? Now, this is the kind of analogy that I want you to now replace by networks. So networks are essentially roads that have certain amount of lanes, or there are smaller lanes, some roads with less number of lanes. This is the highway. So likewise, like the road network, we have our communication networks where you have links that have lesser capacity joining on other links to some link that has greater capacity. And what's traveling along these links, like these cars, are data packets. All right. So this is the analogy, and these are the two questions that I want you to keep in your mind as we progress on. So, so the TCP window size is, we saw that it was actually governed by two constraints so far. One was the bottleneck bandwidth, and the other was the receive window at the receiver. But actually, in reality, when we bring in this third variable, that is possible congestion on the links, we see that the TCP window size must be governed by not two, but three constraints. So you want to keep the sender busy as much as possible, which is your bottleneck bandwidth here. You want to avoid overwhelming the receiver, which is why the receive window is communicated by the receiver back to the sender. It's advertised back. And you must also avoid overwhelming the network. And this is the congestion window or the C wind, right? It's determined by the sender. So now we see that we have three variables or three constraints that must govern the sender's sending rate to the receiver. And that's the topic or the meat of today's class, congestion control. So the C wind is the parameter indicative of current network congestion. Now, there are many questions around this. We'll cover some of the questions, some of the background before we go into actual mechanisms of how this is done. So the window size then is understandable that if we see that this is the one constraint where we want to keep the sender busy, this is the constraint where we don't want to this is the constraint where we don't want to overwhelm the receiver. This is the third constraint where we don't want to overwhelm or add to a particularly congested network, right? And that's the meat of today's class. And of course, I hope that I don't need to point it out anytime that the sender's rate is then thwarted to be the minimum of both of all three of these constraints. So the sender will send to a minimum of whichever of these constraints is less. Why congestion happens on the internet? Important question. So why would congestion happen? Two packets arrive at a router at the same time. Um, the router will let one go onto the wire and will buffer the other one. If too many packets arrive too close in time, what will happen? Too many packets coming in. Packets are going out one packet at a time on the line. The rest of the packets are buffered. What is the one universal truth about every buffer? What's the one universal truth about a buffer? Buffers are, yes, please. Buffers are finite space, right? So if they're finite space, the router cannot keep up. If too many packets come up, it gets congested. What will be caused is because you're then lying in the buffer space for long periods of time. If the queue is long, of course, the delay will be long for the packets at the end of the queue. That means if you are, and that is not a particularly bad scenario, packet delays. Worse is that packet is dropped because you've run out of space. You've run out of buffer space. When you run out of buffer space, that is the ultimate bad scenario where packets will be dropped. So the congestion problem, how do we avoid a set of senders from overwhelming the network? How do we do that? Challenges are huge. You must know that TCP is a point-to-point connection. So it is sender to receiver, feedback going to and fro, data going to and fro. However, all right. So yeah. So you see a network here with many hosts. They're named alphabetically. And there are many links with different bandwidths displayed here. We are going to try and look into the variables that might come into play that the connection is not going to be per se aware of. So what does it depend on? At what rate should host A send traffic? what does that depend on? So host A is trying to communicate with another host via TCP. And you can see that it depends on the destination. A could be communicating to C, it could be communicating to F, it could be communicating to E. It will take various links in different paths where obviously the bottleneck bandwidth is different. We don't know what kind of flows are also accompanying the communication between A and F, what other TCP flows are using the same channels. And that, of course, comes up. It changes with routing dynamics. So between A and E, you can see two different possible paths. There's the blue path and the green path. And with a change in these paths, you can see that the bottleneck bandwidth decreases. Mix of TCP flows will also be different for both the paths. So route dynamics have a big part to play. Also, very, very importantly, it depends on competing traffic. So, for example, we don't know on the pink path from A to F, we don't know how many other TCP flows we are sharing this path or sharing a particular link with. We are unaware. And that is what makes this problem harder because we don't have good knowledge. With the bottleneck bandwidth, we were able to do a good running estimate of it. With the receive window, we were very sure because the receiver was itself advertising that back to us. But here, for other TCP connections that are taking up the same routes or taking up the same links, we are unaware. So this is what makes it very, very hard. And this is competing traffic should immediately put forth the same picture that I had up front, where everybody with their cars were sharing traffic on the big highway and hence the congestion caused. So what are the goals specifically for congestion control? The goals are to prevent or avoid congestion. So, what you want is low packet delay and loss. Of course, low packet delay is very, very desirable. So, if you could prevent or avoid congestion, that would mean that there would be a low packet delay because packets will be flowing more smoothly. And when there is no congestion, you're able to avoid it. That means the buffers will not fill up, and if the buffers on the way do not fill up, that means there will be no loss. You are aiming for high link utilization. So it is not just your aim. This is very, it's not intuitive, it's quite counterintuitive that your aim is not just to avoid congestion. You don't want to congest the links, but you also want to maximally utilize the links. And that is very important. You want to send at a rate that where this utilization is maximal. So these are two opposing goals. You want to be cautious because you want to avoid congestion, but then you want to be here. You want to send faster because you want maximal utilization. And something much more subtle, but that will come along later, you want fair sharing of network resources. So you don't want that there is one particular, this is one channel, and this is actually by order of how much traffic a particular TCP sender is sending. So if in the channel, I have one particular channel sending along with this much bandwidth and one particular channel that is sending along with just this dotted path. And then there is, of course, maybe another and maybe another. You see that one particular TCP channel is uh, grabbing a greater share of the channel. And we don't want that. We want TCP channels or TCP connections to do fair play amongst each other. But this is one of the goals that TCP tries to attain, though this is quite subtle, so it will come back later. How should congestion be addressed? Now, just an over-the-top view, we'll be going into a lot of specifics later. Where should congestion be addressed? Should it be at the host end or at the network end? And by the host end, It's quite simple. At the host end, we mean at the sender or the receiver. And what is at the network's end? What network devices are we talking about? So at the network end, we mean that we are talking to other entities in the network that come in between. Now, what end is TCP implemented at? Can somebody tell me? Is it the host end or at the network devices? Anyone?
Host, host end.
At the host end. See, so we are now actually, when we present the network to be a part of the solution to the congestion problem, we are bringing in the network. So now we're going to be maybe in some way, no specifics here, in some way, now we're going to involve other devices in the network to help us out, to help us solve this problem. All right. So that these are two of our design choices. It could be based on reservation or feedback. So reservation based is preemptive. It's also called open loop. Preemptive means that you want to preempt that there will be congestion and kind of like watch your sending rate. So you don't want to, so let's see the other case, and the first case will become quite evident after that. The second case is it's feedback based, which means it is reactive or closed loop. Reactive means that you take steps once you actually encounter congestion. Once their congestion has already set up in the network, then you react to it and you pull back, right? So if you take the highway example, reservation based or preemptive would be something like some traffic control signal, some traffic monitoring system that will actually be overlooking the highway congestion or the occupancy of the lanes and will somehow give feedback to the channels that are coming in onto the roads and telling them to please divert traffic because you feel that if more traffic came this way, the highways would be clogged. Right? And feedback based is that once the congestion has set up onto the highway, you send back signals and you tell them that please divert traffic. But then congestion has already set in and it will take us some time. So there will be, your service will deteriorate. In preventive, what you're trying to do is you're trying to take action before the problem sets in. So rate control, how do you do rate control? It can be implicit, which means window based. That means that it is automatically as you resize your window. And of course, I hope you remember what window is. We were just talking about it. As you resize your window, you are actually reacting to congestion by simply resizing the window. Or it could be explicit or rate based, where you're actually actively taking information, absorbing information, and you are changing your rate accordingly. Of course, more detail will come in lectures to come. So, what model does TCP use? These are some of the design choices that we've put up here. TCP congestion control actually does host based, so it does not involve any network devices in its congestion control mechanism. It's completely host based. It is feedback based. So that means that it is feedback that is going to come back from the host, right? Not from any devices, but feedback that's going to come back from the host. And it is window based. That means it's implicit according to whatever feedback it receives from the other hosts, the host that it is communicating to. It is going to shrink or expand its window, thereby reacting to either maximizing utilization or curbing congestion. All right. So, any questions so far? I've gone on to the last slide. Any questions so far?
Excuse me, ma'am.
Ji.
Can you go over this model? What model does TCP use thing again?
So we have a few do you see the big capital lettered ors before this? These are all the design choices that are available to us when we try and come up with a congestion mechanism, a congestion handling mechanism. All right.
Okay.
And now we're going to go with a case study, because TCP is the protocol that we're studying. We're going to go with a case study, and we're going to do another one also. We're going to mention another that takes different design choices. But as far as TCP is concerned, TCP, when TCP congestion control was built, these were the design decisions that were taken by the team that made TCP congestion control. Does that solve it?
Yes, makes sense. Thank you.
Most welcome. And we're going to go into a very deep detail of all of this. All right. So from a historical perspective, sending rate only limited by flow control. That means that drop packets, senders repeatedly would transmit, right? Led to congestion collapse. So what happened here is this is just an episode from history. Please realize that in 86, the network was very, very small. And when TCP was actually programmed, congestion had never been encountered in that small network. So the parties that were part of the network were few, and congestion was encountered only later. So congestion control was built into TCP later, and we'll go into that. So in 1986, you have these IMPs, and these IMPs are like these are like routers from which that connect different hosts together. And if you see, the distance between them is very tiny, so it's not a very, very large network. But then if you see that congestion, when it was experienced, there was a very sharp drop in data rates that were actually the rates at which data was actually being communicated. So this rate might read as ridiculous to you, but back in the day, this was a decent data rate. 32 kilobits per second was reduced to 40 bits per second. So this is many factor of 1,000 drop in bandwidth. And that is when congestion was encountered. And that is what started people thinking about what part TCP mechanisms had to play up congestion, right? And then they read into the situation, they read into TCP mechanisms, and then TCP congestion control was programmed into TCP later on. So congestion avoidance and control was done by Jacobson, and very, very highly cited paper, a tremendous impact. TCP implementations use several algorithms proposed in this work. This is the man himself. So a little bit about him. He's part of very important networks research, and it's interesting that he actually was a chief scientist at Cisco, is now at Google. And the competing protocol that we're going to touch upon, we're going to do TCP congestion control in great detail, but the new congestion control variant that we are going to touch upon, BBR, he's also part of that team many years after contributing to the TCP congestion control algorithm as it is. So what does this do? This extends TCP existing window-based protocol, but adapts to, excuse me, apologies. So it adapts and responds to TCP. So you want to extend TCP's existing window-based. It was based on the bottleneck bandwidth. It was based on the receive window, but now we want to extend the windowing mechanism to also incorporate response to congestion. And the approach that was chosen is quite pragmatic, practical, easy to put in, and effective. That was the philosophy behind it. It required no upgrades to routers or applications. So, because routers were not involved in this part, it was completely host based. Routers could needed no upgrades for this congestion control to be put into place. Applications didn't need to make absolutely any changes to them because of this particular patch being sewn in. And all they had to do was to patch a few lines of code to TCP implementations. And that's what makes it very pragmatic. Extensively researched and improved upon. So there are countless variants. We will not discuss a lot of them. There have been many revisions to this algorithm with changing times, but we won't go into them. We will mention some of them along the way as we are covering the mechanisms. There as well as different approaches, especially for data centers and cloud services. And this is where we digress from TCP and move to another approach, which we'll for comparison's sake, which we'll also go into. So let's formally go into congestion control. There's an enormous amount of literature on the problem. It covers many fields, and it is a top 10 problem in computer network systems. There's a recent resurgence of interest in this industry. So it was congestion was observed quite early on. Mechanisms were built into TCP, and then those mechanisms were revised. There were minor revisions that were given to them. But recently, because of new contexts, many data centers have erupted. A data center is a very different environment to the general internet. New application workloads came in, new pressure for high performance computing, cloud services have become ubiquitous. There are new methods, very data communication intensive methods that were brought in by machine learning. So with these new applications, there was a need to revamp congestion control algorithms. And we will briefly touch upon those as well. So let's go into particularly TCP congestion control. And for TCP congestion control, let's go into the implementation. As you can see, we have our familiar window. Let's mark the window. This is the last byte that is ACT, which means the window actually starts beyond the last byte that is ACT. We have the window where there are some sent but not acknowledged. These are the packets in yellow that we call they're in flight. Excuse me. And then this is the last byte that is sent but not ACT. And if you see, the blue are available packets that could be sent, but they have not been handed down from the application. If the application is continually transmitting, we can send the entire window worth of packets all at once, all right? One after the other, not all at once, but one after the other. If you have available slots in the window, that just goes to say that the application has not sent down data to TCP to send. So TCP sender limits transmission. It says that your last byte sent minus the last byte ACT, it should be less than the congestion window. What is the congestion window? Again, just like the receive window and the bottleneck bandwidth times RTT, the congestion window is dynamically adjusted in response to observed network congestion. So network congestion is observed, and the congestion window is it is tweaked according to whatever is observed, and this is implemented in TCP congestion control. Now, the TCP sender, you roughly send congestion window amount of bytes, wait an RTT for ACKs, and then send more bytes. It's like any window that we've done so far, right? We go with the minimum of the 3 constraints that we talked about, but as far as congestion window is concerned, it is no less than any other window that we've done so far. Any questions regarding this? So the congestion window, just like the receive window, is only limiting the number of bytes that should be sent. So if we see no congestion, we will try to broaden the window because we want to fill up the and maximally utilize the link. If we see congestion, we will try to restrict the window or constrict the window to a smaller number of bytes so that we throttle sending rate and let the congestion pass. Any questions here, please? Right, so let's go on with an example. So we have an example, a TCP window size and sending rate. Consider the congestion window size to be 1 MSS. You know what MSS stands for? It is typically the maximum segment size or one packet, typically at connection start. So we're trying to look into TCP window size and its sending rates, and we're considering the congestion window to be just one packet. Assume that this is the bottleneck and not the RWind or the RTT, right? If we assume 1 MSS is equal to 1000 bytes, assume the RTT is 200 milliseconds, the round trip time for the packet to go to the receiver and the receiver to send us an ACK. What is the TCP sending rate? And that's easy enough. The TCP sending rate, because it's 1000 bytes, we multiply it by 8 and divide it by RTT. And the sending rate is 40 kilobits per second. What happens to this rate if congestion window is changed? Do I have any suggestions? What if the congestion window is increased? What will happen to this rate? The rate will be upped or downed?
The rate would increase.
It would increase, right? And vice versa, all right? So the TCP approach to congestion control says that each TCP sender independently runs the following. You pick an initial sending rate, equivalently an initial window size. So you have to start somewhere. So you start with some initial window size. We have to start with some initial values. If you remember, we continually update our RTOs when we doing timeouts, but we had to start with an initial value of timeout. And just like that, we pick an initial sending rate. You try the sending rate at the initial for some time. So you try sending at the initial rate for some time. Do we notice congestion? If we do notice congestion, and we still have to, we've already done that to some extent, but we have to formalize how TCP actually detects or notices congestion. But let's say we put that on the side and we somehow say that we did notice congestion. If we do notice, we decrease the window somewhat, hence the sending rate. If we shrink our window, we shrink our sending rate. If we do not notice congestion, that means that there is still capacity in the network, things are going smoothly, and now we go to maximal utilization. So if this is one goal, if this is congestion control, that's our goal here. Here our goal is the other, which is maximal utilization. And then we repeat, right? So initial sending rate, which means an initial window size. You send for some time. Do we notice congestion? If we do, we somewhat tweak it, decrease it. If we notice no congestion, we increase it, right? And that's how it is. So questions for a TCP. How do we select the initial window size? Big question. How do we select an initial window size? How to detect congestion? How do we notice congestion is there? how to react to congestion. How do we try and fix it when we have detected it, right? Important questions there. So how do we react to congestion? You manage the congestion window size variable, the C wind, but there's a big question, how much adjustment you need to do to the congestion window? Important question. And when to adjust the window size. So our options are that one, the network tells the sender about congestion, right? And there are certain benefits to it. I will let me just go back to the last slide. We are out of time. I would really like if you have some questions, I'm here for you, and I want you to ask your questions. We will continue this in the next class.